Hello everyone and welcome to my new lab. It's been a while since my last proper video, about a year now I think. I know all 37 or so of my subscribers have been worrying, but here I am, I'm back again. I have two projects to show. This video will be for one of those projects and the other one will be coming soon, so be sure to subscribe so you don't miss it. I started building this arm around a year ago, and I never got around to finishing it. Some things came up, and then when those things came down, some more things came up. But it's done now. I had an excellent opportunity last semester to use it as the final project for one of my courses, for my controls class. I was looking through the list of example projects that the professor gave, and one of them said robotic arm control, and I thought that would be perfect, a great excuse to finish this thing. So here it is. It uses inverse kinematics to control where it goes, which I'll demonstrate shortly, and those inverse kinematics are calculated using particle swarm optimization. I'll explain what all that means in due time. For now, let's do a little demonstration. So if I turn it on, it naturally starts at this straight line home position. You can see on the screen a real-time display of where the arm is, and it has some neat controls. Like if you see in the corner, you can see the hand moving, and I don't know how easy it is to see, but there's a tiny dot on that screen moved around with these four buttons, and that is the set position. And if I hit this button here, it tries to move to the set position. And it moved to it. I can move it down lower here. And to reach it. It's not quite. There we go. Sometimes it takes a few tries. That's just a quirk of the algorithm, which I will cover later. But that's the quick little demonstration for now before we start moving into some of the more technical sides of things. This project originally began as a for fun project intended to use almost entirely parts I already had. A good example of that are these DC motors that are the main actuators for the arm. I got them quite a while ago as an impulse purchase, and they've just been sitting around in my motor bin for a while, so I figured might as well use them for something. These are not ideal for this type of application, and I'll explain why in due time. For now, this is a brushed DC motor. This part is the motor. This part is a gearbox. The DC motor on its own spins way too fast and with not enough torque, so it has a gearbox to slow it down and raise up the torque. However, this is still not enough for my application, hence the need for another gearbox to go on the end, which I have right here. This is a little test one I made, or a demonstration one I made with a cutaway in it. But this is the gearbox. I designed it and 3D printed it. It is a two-stage planetary gearbox, 2 stages. And in total, it has a 20-to-1 reduction. So for every 20-ish turns of the actual motor here, the output shaft turns once, so I get a lot more torque. It is a planetary gearbox, meaning if I take this apart here, you can see there in the middle, that is the sun gear, and these here are the planet gears. And what happens is, when this goes in here, when the motor turns, the sun gear also turns, and that kind of creates like a torque against the planet gears and against this ring gear on the outside, and that causes the planet gears to orbit around the sun gear. And it is that orbit that this part called the carrier kind of takes, and that's the output of the motor. So I can demonstrate that real quick. So you can see that the planet gears are rotating, and as they're rotating, they're also orbiting around in circles, and that's the output. In this case, instead of the output shaft, this is a second sun gear, which goes in here to act as the sun gear for the second stage. And you can see its orbit is a lot slower than the first stage. So using that, it compounds and it just makes it even, individually, if I take this, individually this here is like a 4.5 ratio. So for every one turn, for every 4.5 turns of the motor, this turns once. And then this one, it's the exact same. So in total, it's for every, 4.5 squared, which is just a 20.5, I think. For every 20 or so turns of this turns once, which means we get 20 times less speed, but 20 times more torque, which is perfect for this application. Let me turn that off, it's a little bit loud. So yeah, that's the gearbox that I printed. It turned out very nicely, and I'll probably be using this kind of design for other projects. It's a pretty nice little actuator, but there are some other things that need to go into the mechanical design in order for this type of motor to work, and I'll explain that now. As previously mentioned, there are some additional things that need to go into the design to allow for this type of motor to work in this application. This is just a regular DC motor, so it can only do two things. It can spin in one direction or spin in the other direction. This is fine enough, but along with that, I require some form of feedback. In order to tell this joint to move to a certain angular position, I need to know what position it's already at. And that's what this doohickey here does. This is a potentiometer. And I have some right here so I can show you what it looks like on its own. So this here is a potentiometer. This shaft can rotate, and as it rotates, it will output a voltage corresponding to the angle that the shaft is at. So there's a bolt here and another one on the other side that essentially pinch both sides of the shaft and ensure that it rotates with the joint. And that is how the position feedback is handled by the arm. And so that way, in the code, there's essentially 3 different functions that each control one of the joints, where it just acts like a nice little box. I send in an angular position, and then it will just move that joint to that position. And that is very convenient to have that separate like that in the code. I will not go too much into how the actual code for that works. If you want to know more, you can look up a PID controller, because that's what it is that controls these. Instead, I'd much rather go into some more detail about the actual algorithm that does the inverse kinematics and how that operates, because that's the kind of key aspect of this project. Particle swarm optimization. And I will get out my whiteboard and I will explain that in some hopefully clear detail. Essentially what the arm is doing, what the algorithm that I have programmed is doing, is called inverse kinematics. Essentially, we take a set of coordinates, a point in space, and turn it into a set of 3 angles, such that when the arm moves its joints to those angular positions, its end is at the point we specify. This is rather difficult with anything more than 2 angles, because it is not uniquely algebraically solvable. And I might get that a little bit wrong. Maybe some math person in the comments will say, I don't know the right way to word it. Essentially, you cannot come up with like a pure equation where you just stick in two numbers and get out these three numbers. So I have opted to use a fancy algorithm called particle swarm optimization. And what that algorithm does is it does this for me. I give it two numbers, I give it this coordinate, this point in space, and it spits out these three angles. And the arm moves to those angles, and that is what you saw at the demonstration at the beginning of this video, is the arm moving to points specified using this algorithm. So I will go into some detail now as to how that algorithm actually works, because I think it's pretty cool. Particle swarm optimization, as the name might imply, involves some particles. And these particles are able to move around and stuff like that, some pretty cool things. But these particles need a space to exist in. So here I have this two-angle version of the arm, basically. I could do it for three, but I don't want to have to draw cubes and stuff. So essentially, this space has two axes, one representing the first angle and one representing the second angle. And any point in this space, like this one here, represents a configuration of the arm. So in this case, we have theta 1, 90 degrees, theta 2, 45 degrees, and that's encoded in this point. And so that is the same as this, as the arm in this position. So this state space, every point in it corresponds to some configuration of the arm. And any configuration of the arm has its end at some point in 2D space. And essentially what we can do is for every point in this space, we can calculate how far off the endpoint of the arm is from the set point. So essentially, this is the state space with every point representing some configuration of the arm, and every one of these points has an error value associated with it. So that error value tells us how different, like how far off that configuration is from the desired end position. And using that, we can then get into the particles and the complicated part of this. So now that we understand the concept of the state space, where every point in that space corresponds to the state, to a state of the arm, and that if we have a set position, every point in that space also has an error value associated with it. So in this case, we'll just have the simple theta 2, theta 1, 0 degrees, 0 degrees, 180, 180. The joints can't really move beyond this. They can't go 360, so this space we cut off at 180 degrees. That way it just ensures every point is actually reachable. Now we have this space and we know how the error value works. So it might be a little bit difficult to explain how this algorithm actually functions. It is a little bit arcane. So essentially, if we have a point in two, like if this were the arm, and let's just say it's at some random configuration right now, but let's say that the set point was right here, and that would correspond to it going straight up and down, but we'll go through how the algorithm actually finds that that is the case. We essentially put down some random particles in the state space. Each one, like, we'll just have two of them for now. And these two particles start with some random velocity associated. So this one might go this way, this one might go that way. It's all random. And every time step, they adjust their velocity by first looking at what is the error value associated with this point, and is this the best point I've been to? That's what the particle asks itself. Is this the best point that I have been to? And if it is, it will remember that. And along with that, it will ask, is this the best position? Is this the lowest error value position that the whole swarm has been to? And if so, that gets remembered by the whole swarm. There's like some swarm intelligence thing going, a hive mind going on here. So being remembered, the whole group as a whole remembers what the group best is, and it also remembers what its own personal best is. And to just kind of give a little bit of a spoiler, for this position where it's straight up, the lowest error value will be in the center, obviously, 90 degrees, straight up. And the error values will kind of grow as you move outwards from that point. So in this case, well, they're both kind of the same distance, so the group best is kind of tied, but let's say this one has the group best. And their personal best is like the same right now because they haven't moved at all. So they'll kind of just move. And then they'll look at everything again, this step, and they'll see, okay, so this guy will know that this is his personal best. He'll remember that. This is this guy's own personal best. But also, this is the group best. So this particle wants to move towards its personal best, which in this case is its own position, so it doesn't really affect much. But at the same time, it wants to move towards the group best, which would be this way. And there's a little bit of randomness associated every time they change. There's a few random numbers just to add a little variation. But essentially, this guy wants to move more towards here, and then this guy, he's not really going to move much at all because he's in a good spot right now. So let's just pretend like he stays still. And they move again. This guy moves here, and this guy kind of stays still. And then they're like, whoa, okay, so this is the group best now. This is the place to be. And this guy's kind of content because, you know, he's going to move a little bit. We'll just pretend like he's going to chill. It just makes it easier to explain. He's going to chill there because that's his personal best and the group best. So he can, in his mind, that's probably the best place there's ever been. And so then this guy, he's going to want to move towards that. So he's going to kind of move towards it. And whoa, now this is the group best now. This is the best place. And so essentially, as that goes on, and especially when there's more particles, in the code I wrote, I'd have to check again, but I believe there's like 10 particles. And so as all the particles move around, they'll naturally end up converging on the point of least error. And after a certain number of time steps, I believe it's only 50 steps in my code. So in the code I wrote, after 50 steps, we can just see whatever the group best is and just take out the group best. And the group best is a coordinate. It is a set of, in this case, 2 angles. And we can see in this case, the group best, it'll converge here, is 90 degrees and 90 degrees. So we can just take that out and just send that to the code that controls the motors, and the arm will then just move to where it needs to go. It'll go, okay, so the group best is 90 degrees and 90 degrees. So let's just do that. And that's all it's doing, really. Every time we want to change the position of the arm, you saw on the screen at the beginning, I can move where the set point is in space. And once I have the point where I want it, like let's say like here, I hit a button, and then this algorithm runs. The particles are spawned in, and they all kind of move around. They'll converge on whatever set of angles gives the least amount of error. And then we just send that set of angles to the motor control code, and it just moves the arm there. So it's a pretty cool algorithm in that respect. And It's a square right now with 2 angles, but for the actual arm with 3 joints, it would be a cube. And the interesting part is that this works, in theory, for any number of joints. However, the computation quickly goes up as you add extra dimensions, because for every joint, you get another dimension in this space. So, you know, this is a cube, and if you had 3 joints, it'd be, no, this is a square, and if you had 3 joints, you get a cube. You add a 4th joint, and you get a hypercube, and then for every joint you add, you get a higher dimensional hypercube. So the downside is you do lose the ability to conceptualize what they're actually doing as soon as you leave the 3rd dimension. But in this case, it's pretty easy to visualize. You're moving around and finding the point with the lowest error value associated with it. And you can easily adjust the number of time steps, the number of particles, and things like that to try to, the more time steps you add, the more you're guaranteed to kind of land at this point. But you can get away with less. In my code, it uses 50, but I did test it out with like 30 for a while, and it was pretty good. And the number of particles you can easily change too. Obviously, the more particles you add, the more computational heavy it is. But for the most part, it's very adjustable, so it's a very cool algorithm. I do have some, there have been a lot of good resources I have used to learn about this algorithm. I will link them in the description because I don't have any fancy like animation software, nor the skills to use software like that. So this might not be the best description of how this algorithm works, but there are lots of good resources out there, but it's a very cool algorithm. So that's essentially how the algorithm works. A bunch of digital simulated particles moving in a swarm with swarm intelligence converging on the right point. And I think that's pretty cool. Now, to sort of bring this all to a conclusion, I am very grateful I was able to use this as a final project in my class. It was a very good opportunity for me, and I learned a lot from this. It's a very interesting project, very interesting code involved. I had never heard of this algorithm before. I was simply going around on YouTube looking for videos on how to do inverse kinematics, and I just happened to see some guy upload. He had a video explaining the algorithm very well. I'm going to link that video in the description. It was very useful for me. So I quite enjoyed the whole swarm intelligence aspect of it, of the algorithm. I thought it was cool that you can have these particles moving in their own way, but they also move as a group and sort of converge together. The fact that it converged at all was very interesting to me. It was very rewarding to see the algorithm actually work. I do plan on having some more projects in the future involving like swarm type things, though that's a long ways off. There's plenty of other things in the works before that. So yeah, overall it was a really cool project, and I do have more projects to show. I have one more project right now to show. That will be for a future video, so please be sure to subscribe. I can give you a little teaser of it right now, actually. So if this thing looks interesting to you at all, or if you can even sort of guess what it is just by looking at it, you might be kind of interested in where this is going to go. So please be sure to like and subscribe, and thank you for visiting my lab, and hopefully see you in the next video.